Okay, so in this lesson, we're going to continue looking at how to calculate the resultant of two perpendicular vectors and how to resolve a vector into two perpendicular components. So firstly, we're going to introduce a new set of notation, and this notation, this new idea is called the standard basis. So what we have now is the vector I is a vector of length 1, the vector j is a vector of length 1, and the vector k is a vector of length 1. That is, the magnitude of each vector is 1. The vector I is perpendicular to the vector j is perpendicular to the vector k, and the vector k is perpendicular to the vector I. This is called the standard basis. So graphically, it's a bit like an XYZ three-dimensional image you should be having in your mind. So you can see here, there's O, the origin at the center, because I, J, K are position vectors. Since they reference only one point, OI is 1 unit, OJ is 1 unit, OK is 1 unit, and you can see there OI is perpendicular to OJ, OJ is perpendicular to OK, and OK is perpendicular to OI. This is the standard basis. The advantage of this is like a universally set basis, so it basically means that vectors can be reconstructed by referencing this basis. So in other words, if I have a vector in my head that I want you to draw, I will assume that you know what ijk are. So for example, I just need to tell you how many i's, how many j's, and how many k's are in my vector, and you can reconstruct the vector exactly. For example, I want you to draw 3i plus 5j plus 2k. So you can see on the I direction, I go out 3 units. In the j direction, I go out 5 units. In the k direction, I go out 2 units. I add these 3 vectors together, and the red vector is the vector that I asked you to draw. Now, this is three-dimensional, and it's difficult to draw 3 dimensions in 2 dimensions, so you need to picture this arrow coming out of the screen towards you. The advantage is they obey basic algebra rules that you would know for a long time now. For example, to add these 2 vectors together, 3i plus 5j plus 3k, and 2i plus 4j plus 2k. In this question here, it is as straightforward as adding the i's together, adding the j's together, and adding the k's together. So you have 3i and 2i, 5j and 4j, 3k and 2k. So you get 5 i's, 9 j's, and 5 k's. Now, suppose we have our vector xi's, yj's, and zk's. We can use Pythagoras' theorem to calculate the length of this vector. The length of this vector will just be square root x squared plus y squared plus z squared. If the vector is two-dimensional, we will get square root x squared plus y squared. Now, the proof of the two-dimensional case almost goes without saying. Or what I mean is, the proof is something that you would have seen a long time ago. It's not a particularly big proof or difficult proof. In fact, Pythagoras' theorem is one of the basic theorems you have for geometry and trigonometry. So this two-dimensional case doesn't need me to say much about it. Three-dimensional case, though, you could almost guess it from the two-dimensional case, and the proof, I think it's better if I leave the proof for you to try. See how you can get on with that. You can assume that the two-dimensional case is true. For example, let's have a look at the question now. What is the length of the vector 3i plus 5j plus 3k? So the length, the magnitude of this vector is square root 3 squared plus 5 squared plus 3 squared, which is square root 9 plus 25 plus 9, which is square root 43. The vector xi plus yj is 5 root 2 units long and makes an angle of 45 degrees with the I vector. What is x and y? And the convention here is you start at I and head towards j, and this is a positive angle here. In other words, positive angles go counterclockwise or anti-clockwise. So we're looking for x and y, and we know the length of the red line there, the red vector. So we need to think back to basic trigonometry, middle school trigonometry, class 1 or class 2. The sine is the opposite over hypotenuse. So here, the sine of 45 is y over 5 root 2, which results in y equal 5 root 2 sine 45, which is 5. Likewise, the cosine is the adjacent over the hypotenuse. So cos 45 equals x over 5 root 2, and so x equals 5 root 2 cos 45. So in this particular case, you get x is 5 also. So we have found the answer. The red vector is 5 i's and 5 j's added together. Now, the next idea we'll look at is something called a unit vector. So if we're given the vector xi plus yj plus zk, we can shrink it down or expand it up to make it have length 1. For example, if my vector has length 10, and if I multiply my vector by 1 over 10, I can shrink it down to make it have unit length 1. If my vector had length, let's say, a half, then if I multiplied my vector by 2, I'd expand it up so that it has length 1. So in other words, provided that the vector isn't 0 in length, you can always multiply it so that it expands, or it shrinks, or contracts, so that its length is 1. And how do you do that? Well, it's not too difficult, it's rather easy actually. To find the unit vector, the vector of length 1, which we represent as or with a little hat symbol above it, all you have to do is take the old vector and divide it by its length. And that's all. So let's have a look at an example. So make a unit vector from the vector or equals 3i, 5j, and 3k. So the unit vector is the original vector divided by its length. So it's 3i plus 5j plus 3k divided by square root 3 squared plus 5 squared plus 3 squared, which is 3i plus 5j plus 3k divided by the square root of 43. So the answer is 3 over root 43, 5 over root 43, and 3 over root 43, I, j, and k. Okay, now we're going to introduce a new idea. Up to this point, we have a way of adding and subtracting and multiplying vector by a number, by a scalar, to make it bigger or smaller, or change its direction if we multiply it by -1, etc., etc. Now, let's imagine we have this vector or1, which is x1i, y1j, and z1k, and the vector or2, which is x2, y2, z2, ijk. We define the dot product, or the scalar product, so I actually call it here the dot scalar product, just to get all the possible names covered. We define the dot product of or1 vector and or2 vector as x1, x2 plus y1, y2 plus z1, z2. So in other words, to dot product these two vectors, you multiply the x's plus multiply the y's plus multiply the z's. And what you notice is that when you dot or1 and or2, you get a number, you get a scalar, not a vector. So dotting two vectors together makes a single number. What's very useful about the dot product is that if the vectors are perpendicular, then this dot product will be 0. And if they're not perpendicular, then it won't be 0. It's actually a very useful, quick way to check if two vectors are perpendicular or not. And a very simple way too. Calculation is not difficult here. The advantage though for us right now of using the dot product is that it allows us to rewrite the vector in a new basis. For example, up to now we're using I, j and k, or maybe I and j if it's 2 dimensions. But we'd rather use the vectors r1 and r2 and r3. So we're using I, j, k, and that's fine, but we'd rather write our vector in terms of r1, r2 and r3. So it's a new basis, a new system. This is easily done if the vectors r1, r2 and r3 are perpendicular to each other, and even easier if they are unit vectors. So the first thing you would want to do when using your new basis is to make sure that they're unit vectors first. This makes things a lot more convenient. And then your new vector would be written in the form of AR1 plus BR2 plus that should say CR3, of course. AR1, BR2, CR3, not CR2. So the question is, okay, well, what is the A, B, and C? How do I find these new coefficients, these new numbers? Well, provided that the basis, again, is perpendicular, you have a very simple formula. The A is just r dot r1, the B is r dot r2, and the C is r dot r3. So this is a very straightforward way to calculate the ABC. You just need to use the dot product, which isn't very difficult. It's really just a multiplication and addition of numbers. Let's have a look at an example here to really illustrate what I'm trying to say. Express the vector r equals 4i plus 5j in terms of the vector r1 equals 2i plus 3j and r2 equals 3i minus 2j. So in other words, we don't want to write r in terms of I and j, we want to write it in terms of r1 and r2. Well, first, we need to calculate the length of r1 and r2, and in this particular case, they're both square root 11. So the unit vector r1 is 2 over root 11i plus 3 over root 11j, and the unit vector r2 is 3 over root 11i minus 2 over root 11j. Next, we need to dot the vector r with these two unit vectors we've just found. So r dot r1 will be 4 times 2 over root 11 plus 5 times 3 over root 11, which is 23 over root 11. And then we do r dot r2, which is 4 times 3 over root 11 minus 5 times 2 over root 11, which would be 12 minus, I think I have a sign mistake here. 4 times 3 is 12. 5 times 2 is 10. 12 minus 10, that should be 2 over root 11. I better double check the first one here. 4 times 2 over root 11 plus 5 times 3 over root 11. So that's 8 over root 11 plus 15 over root 11. So that's fine. So it looks like I have a sign mistake now, unfortunately. So I have my answer. R equals 23 over root 11 R1, and that should say plus 2 over root 11. So very sorry about that. I have a sign mistake. I typed in the wrong sign, I guess. I will make the changes into the file. So when if you want to download the notes, the changes will be there. So I have to fix that sign. And then I have to change an R2 into an R3 when I was typing earlier with the new basis. So sorry about that.